Welcome to Chemistry, Characteristics of Matter, Section 6.2. Here's the objectives. Be able to describe a standing wave and be able to state the Heisenberg uncertainty principle. Those are the two main things we want to get out of this section. All right, first of all, let's talk about this guy named Louis de Broglie. And he figured that if waves can have properties that were particle-like, then he figured, well, the opposite must be true too. It could be true that particles have wave-like properties. So that was kind of his idea, that you could take some kind of object, any object, and it would also have wave properties. So before we kind of get into that in a little more detail, let's talk about what standing waves are. And a standing wave is where you have a wave that the crest and the trough kind of are in the same place. So for instance, think about if this is a rope and I shake the rope and the wave goes across, hits here, and then comes back, so that here's my crest, here's my trough, and I can just keep doing that. If I have that right rhythm, I can do that. Or I can do it twice as fast, and I get it like this, and it just stays like that, and so on. So there's 3, cycles, 4 cycles. Here's an example down here of it with a machine, and you can see how, this wave is just, there's multiple waves in here as we go. That's a standing wave, and you've probably done that with a rope if you think about shaking it so that it looks like there's these areas that don't move at all. Those are called nodes. Then you've created a standing wave. So you've probably done that. Oops, wrong guy. All right, so Heisenberg is this guy. He comes up with this idea called the uncertainty principle, and he says, well, you know what? It's impossible to know precisely, about the electron exact precise location and its velocity at the same time, because when you're measuring that, what he says is that you're actually moving it. So every time that you try to figure out exactly where it is or exactly how fast it's going, you're actually changing that. And that's true about any kind of measurement we make. The truth is that most of the time those don't matter. So for instance, if you were trying to find the temperature of something, you stick a thermometer in it to figure out what the temperature is. That thermometer is actually going to change the temperature of the substance you're measuring, but it's negligible. However, if that was just a drop of water and you're putting that thermometer in there, now that could make a big difference. Well, when we're talking about small things like electrons and we're shining light on them, the light has enough energy to move them, to make them accelerate, to make them move from where they were, and that changes the velocity or the position of them, and therefore we can no longer tell exactly where they are. Okay, so we were talking about how we have, de Broglie has these ideas that particles could be waves. So this guy named Schrödinger says, well, let's assume that the electron is a wave, and let's see what happens. So he starts to work on these equations, and you can look at this, and these are some pretty complex things. And notice they're a little more complex than most of the equations we do, and in fact they're so difficult that you can't really solve them. Instead, they usually just take a computer and get an approximation of them, but as far as actually solving the equation, it's pretty tough. So they just use a computer to kind of approximate what the answer would be. If you're interested in looking at this kind of interesting stuff, go take a look at Schrödinger's cat, find out a little bit about that, just kind of interesting thing. Kind of a paradox idea that he had that goes along with this. Okay, so talking about these electrons now as waves, this is where quantum mechanics comes in and says, well, quantum mechanics says the wave has to fit exactly in the atom. So for instance, if we look at this one on the right, we've got this wave, and notice that we get all the way around the wave and it doesn't quite fit, doesn't meet, so it would overlap and go, well, quantum mechanics says that just can't happen. It just doesn't happen like that. So the only thing that works here is if those waves, the perfect, integer amount of waves fits around that circle, around that, for that electron. So waves can only occur if there's a whole number of waves that goes around there. And this kind of explains, Bohr came up with the idea and says, hey, there are energy levels, but he didn't really explain why, didn't know why. This kind of explains why those electrons have to be in those particular levels, because if that electron is out here, that wave isn't going to quite match up, it's not going to work. So there's only certain amounts that will work to fit into that particular size. So this explained the Bohr model a little bit better, explained why there were energy levels. Okay, so in summary here, we talked about the Heisenberg uncertainty principle. Can't know the exact location and motion of an electron at the same time. We could know its a location. We can figure that out, but then we don't know how fast it's moving, or we can know its velocity, but we don't know exactly where it is. Electrons can be viewed as if they were a standing wave. The reason that an electron in an atom may have only certain levels is because those electrons will form those standing waves in that certain volume that you have. They don't fit otherwise. And the solution to Schrodinger's equation gives us a lot of information, very difficult solution, but gives us a lot of information about the electron clouds and what they would look like. And that is it.